In this video, we will introduce electrochemistry through a discussion of oxidation numbers. First of all, let's define electrochemistry. Well, electrochemistry is really just a study of how electrons, and therefore electro, are transferred from one chemical species to another. Many of the reactions that you've been doing in grade 10 and Chem 20, such as formation reaction, decomposition, single replacement, and double replacement, are really just electrochemical reactions. All electrochemical reactions are also called as redox reactions. Redox is really just an abbreviation for reduction and oxidation. And again, a redox reaction is a chemical reaction in which electrons are transferred from one chemical to another. There will always be one chemical receiving an electron, and there will always be one chemical donating electrons. The first important concept in electrochemistry is the concept of oxidation numbers, or ON. It is really just a positive or negative integer, a whole number, that corresponds to what we call the oxidation state. Now, this is not a real state, but it's a fictitious state. An oxidation number is just a way of sort of counting electrons or electron bookkeeping. And these are not charges, however, they're just a fictitious way that we can designate who has the electrons and who's losing an electron. Now, if you remember from earlier courses, if the number of protons equals the number of electrons within an atom, that atom is neutral. We can now say the oxidation number for that atom is 0. However, let's say you have a 1 electron more than you have protons. Well, in the previous courses, you know that the atom is now an ion. It's a negative ion. It has a charge of -1. And now we can say the oxidation number of this atom is -1. It has gained an additional electron, and because electrons are negative, the oxidation number is -1. In fact, we can use oxidation numbers to compare atoms to see who or which atom has more electrons and how many more electrons than usual, and on the other hand, which atom has lost electrons and how many electrons it has lost. The greater the negative number, the more electron it has gained, and the greater the positive number, the more electron it has lost. Even though we can use oxidation number to sort of keep track of electrons, remember these are not true electrical charges, and we're going to look at how we're going to designate oxidation numbers in the following few slides. The first rule for assigning oxidation number is that the oxidation number of all elemental atoms is 0. So things like oxygen, nitrogen, even metals such as sodium, magnesium, they all have an oxidation number of 0. The example on the PowerPoint is that chlorine has 2 atoms of Cl in one molecule, but each atom, because we're going to assign oxidation numbers to atoms and not molecules, is going to be 0. So other things such as iron and sulfur, all those atoms in those molecules have an oxidation number of 0. Our second rule is very similar to our first rule, and our second rule states that the oxidation number of simple ions is just equal to the charge of the ion. So here, remember, simple ions are ions with 1 atom only. The other type of ions are polyatomic ions such as phosphate. So this rule does not apply towards phosphate. So some examples is chromium 3+, the oxidation number of chromium will be +3. Notice here, even though ions have a charge of 3+, the oxidation number, being an integer, is +3. For sulfide is -2, and for iron 2+ is +2. Other examples we could do would be sodium ion has an oxidation number equals of +1. Another one we could do is, let's say, calcium ion, Ca2+. Its oxidation number will be +2. The third rule is that fluorine is always assigned a value of -1. This is just a corollary of rule number 2 because fluorine ion, being F-, automatically has an oxidation number of minus 1. So even in a complex molecule such as S2F10, fluorine is going to be minus 1. Even though it's not an ion, it's a molecular compound, but its oxidation number is still negative 1. Our fourth rule is very similar to our third rule, and our fourth rule states that the oxidation number of oxygen in compounds, so not just ionic compound but molecular compounds as well, will be negative 2, except if it's a peroxide, in which case it will be negative 1. So our peroxide example is hydrogen peroxide. The oxidation number for oxygen in hydrogen peroxide is minus 1. But for all other compounds, molecular or ionic, the oxidation number for oxygen is minus 2. Our fifth rule is similar to our fourth rule and our third rule, and our fifth rule states that the oxidation number of hydrogen in any compound is going to be positive 1, except in the case of metallic hydrides, where it's going to be negative 1. Metallic hydrides are cases where hydrogen is bonded to any metals. And any metals, as you recall from grade 9 and grade 10, are compounds that are listed on the left-hand side of the periodic table. So in our first three examples here, we have water, H2O, a molecular compound, ammonia, another molecular compound, and butane, another molecular compound. Because they bond with non-metals, the oxidation number of hydrogen for all of these cases is positive 1. However, in our fourth and fifth example, we have sodium hydride and calcium hydride. We note that sodium and calcium are metals, so our alternate rule kicks in. That tells us that the oxidation number for hydrogen in this case is going to be minus 1. Our sixth rule, and probably our most important rule, is that the total of the oxidation number of all the atoms in a molecule, in a neutral molecule, is 0. So for example, let's look at dinitrogen tetrapenta oxide, N2O5. So we know that the sum of all the oxidation numbers from all the 2 nitrogen atoms and your 5 oxygen atoms must be equal to 0. Well, earlier we said the oxidation number for oxygen is always going to be minus 2. But we don't know what is the oxidation number for nitrogen just yet. However, we know there's 2 nitrogens, so that when we determine the total oxidation number of the molecule, we have to multiply the oxidation number by 2. We know there are 5 oxygens, so we need to multiply our oxidation number for oxygen by 5, so 5 times 2. And all of it, the sum of it, has to be equal to 0. So now we can simplify our math. So we have 2x minus 10 equals 0. And then solve for x. X is 5. So then we know that the oxidation number of nitrogen in our molecule here of dinitrogen pentaoxide is positive 5. Let's look at another example here on the slide. P4O10 tetraphosphorus decaoxide. We know there are 4 molecules of phosphorus, but we don't know what the oxidation number of the phosphorus is just yet. We know there are 10 atoms of oxygen, and each oxygen is minus 2. And we know that at the end of the day, all of the numbers here have to add up to 0, or oxidation number add up to 0. So what could possibly go into this blank? And the only integer that can satisfy this equation is positive 5. So therefore the oxidation number for phosphorus is 5, positive 5. Let's look at a third example that's not on the screen. Let's say we have ethane C2H6. Well, we know hydrogen has an oxidation number of positive 1, and there's 6 of them, so 6 times positive 1. And we have 2 carbons, so plus 2 of an unknown oxidation number, and everything has to add up to 0. Therefore, if we do some math in our head, well, we have positive 6, and then so that we need -6 charges to balance everything out. But there are 2 carbon atoms to carry that -6 charge, so each carbon atom, the oxidation number of each carbon atom must be -3. And our last point on this slide here is that the oxidation number of halogens in compounds is usually being the key word, is -1. Previously we said fluoride and fluorine, in all compounds is -1. We can sort of extend that rule to all halogens, but we have to keep in mind this is a rule that is usually true, not always true. And then we have a couple more examples here. We have S2Cl6. We know chlorine has an oxidation number of -1, but there's 6 of those atoms. We have 2 sulfides carrying an unknown oxidation number. Solving for X, we find that X, or the oxidation number of sulfide here in this case, is +3. And the last example of ammonia, we have 1 atom of nitrogen and 3 atoms of hydrogen. We know hydrogen is +1, therefore X, or the oxidation of nitrogen, must be -3, so that the entire molecule have a oxidation number of 0. And our last rule, which is similar to our rule number 6, is that the total of the oxidation number of all the atoms in a complex ion, or otherwise known as a polyatomic ion, is equal to the charge of that ion. So for example here we have permanganate MnO4-. We know oxygen has an oxidation number of -2, and there's 4 atoms, so 4 times -2, and we do not know the oxidation number of manganese. However, we know that permanganate MnO4 has a total charge of -1. Therefore, we no longer put in 0 as our final oxidation number, but now -1. The math is still the same, and when we do the math, we find that the oxidation number for manganese is +7 in the permanganate ion. Similarly, we can do something a little bit more complex. We can look at dichromate, Cr2O7. Again, there are 7 atoms of oxygen, and therefore, we know each oxidation number of oxygen is -2, and we know there are 2 chromium ions, or atoms, and we do not know the oxidation number of that yet. However, we know the sum of all the oxidation number has to be -2 because that's a charge of the dichromate ion. And we do our math, we find that X, or the oxidation number of chromium atom, is +6. And there's a couple more examples for you to look at on your own. However, notice here that we have a molecule with 3 different atoms here for C3H7Br. We know that the charge oxidation number for hydrogen is +1, for halogens such as bromine is -1, and then we don't know the oxidation number for carbon, but we solve it and we see that it's -2. Now recall that we said oxidation number is a fictitious way of sort of bookkeeping. It's actually a bookkeeping way of counting electrons. So hydrogen has the highest, or the most positive, oxidation number. So we say that hydrogen is most highly oxidized, which we'll get to on the next slide. And carbon, because it is the most negative, or if you want to talk about the least positive oxidation number, it is the highly reduced. It possesses the most electrons of all the atoms in that molecule. Here's a summary slide of how to determine oxidation number for each atom in a molecule. The first step is to assign common oxidation numbers. So again, the oxidation number of hydrogen for molecular compounds is going to be +1, but for ionic compound it's going to be -1. Oxygen is going to be -2, except the case of peroxides such as hydrogen peroxide, in which case the oxidation number of oxygen is -1. Any halogens, they're usually going to be -1. Step 2 is to remember that the total of all the oxidation number of all the atoms in a molecule or ion equals the net charge of that molecule or ion. And the third step is that if you have any unknown oxidation number for any atoms, you can determine it algebraically because of step 2 and step 1. Now, it'll be okay if your oxidation numbers do not come out to actual integers, but rather fractions. That's okay, because remember, oxidation number is not a true electrical charge, it's just a matter of bookkeeping. So let's say you have an oxidation number of positive 2/3, that is perfectly fine, you haven't done your math wrong. And the very last slide, a couple more important terms. We said a redox reaction was just an abbreviated form of saying a reduction oxidation reaction. Well, we need to define what is reduction. Well, reduction is a chemical process or a reaction where a particular species, whether an atom, molecule, or an ion, gains electrons. That means that atom gets more negative, and if it's more negative, the oxidation number goes down. On the other hand, oxidation is a reaction or a process that involves a loss of electrons. If you lose electrons, you lose negative charges. That means that our oxidation number is going to increase or get more positive. So our ON goes up. Now, oxidation and reduction reactions always are paired together. You cannot have one reaction happening by itself, because if you, let's say, gain electrons, you have to have a source of that electron, and the source of that electron is the oxidation reaction. So oxidation reactions and reduction reactions are always paired. One chemical species gains electrons, the other chemical species loses electron. The way to remember this is that there is a mnemonic called oil rig. OIL, it stands for oxidation is loss of electrons, and rig, reduction, is gain of electrons. A couple more important factors on this slide here. A reducing agent is something that actually oxidizes itself or becomes oxidized, whereas an oxidizing agent itself will get reduced. It will gain an electron. Well, this is a slightly confusing term unless you pause to think about it. An agent, right? It's not the thing or the molecule that does the whatever it's describing. It helps someone else do it. So for example, let's think of a travel agent. Well, the travel agent doesn't go on vacation himself, but the travel agent helps you to go on vacation yourself, right? So remember, a reducing agent helps someone gets reduced. In that process, it becomes oxidized, and an oxidizing agent helps someone else or helps another chemical gets oxidized, and in turn, when it does that, it gets reduced itself. It's absolutely key that you keep these terms clearly distinct from another and you know what they mean.